All right, folks, time to go. The answer key is live. I've put it in the chat. You can always change the kind of O2 assessment to O2 answer key and get the answer key on that website. So I'm just not providing links because, you know, it's the answer key. It's supposed to be secret. But you should always be able to change assessment to answer key and get the answer key. For those of you that are astutely observing this and thinking that you might be able to do that for the next assessment, you can't. So I have been studiously making sure that I only upload this after the due date for your submissions. So okay, so the first thing that I'd like to talk about is the first problem, 1.1. So fit a regression predicting earnings by height for, can everybody see my screen? Yes, cool. Okay. Zoom in a bit. Yes, I will. Actually, let me share just the browser. Yeah, I know everybody's got a differently sized screen. So I was dumb and I included this was promoted variable, as I think Matt and James pointed out early on. So yeah, this wasn't in the data, by the way. So doing data science mentally, fit a regression predicting height for two sexes, as well as the overall effect of height on earnings. Then, with these models, does an extra meter of height have a statistically significant impact on earnings for men? How about for women? Are the impacts statistically different from one another? Okay, so to start off, yeah, there might have been some other things, like some people noted that there was like 9 in the Hispanic column, which meant missing. So yeah, there might have been some issues with the data that I didn't kind of fully clean it up before I gave it to you, which, you know, that's my fault, but then also I guess it's good training that the data set sometimes might not satisfy the assumptions that are stated about it. So here, the first thing I'm doing is I'm loading the libraries that I might need. I actually might not need to load Broom because it could be in the tidyverse, I'm not sure. But I'm reading in the data, as many of you have done successfully many times now. And the very first thing I'm doing is centering my height variable. Okay? I'm also making sure that the things that I'm using as factor variables are turned into factors explicitly, so I can control them at this juncture. Okay? And what I had intended for you to do in section 1 is to fit a model which only talks about the male data, a model that only talks about the female data, and then a model for all of the data. Okay? This is the analog to the Gelman reading when Andrew talks about the male model, or sorry, the no pooling model, which only considers the group that it's talking or that it's interested in. So a no pooling model is a model that's just fit on every individual group. And so the male model and the female model are two examples of the quote unquote no pooling model. They don't communicate anything about their results. The all model is reflective of the complete pooling model, and that is kind of everything that's available is just used to construct one estimate. Now, you could have done this in a lot of different ways. I chose instead to do the broom tidy function. and then pass it the different kinds of models. And I also gave them names so that I could view them in a nice little table. So I'm rbinding, that function, you should have seen it before. If you haven't, rbind stacks together data frames by their rows. So they need to have the same columns, but then they just kind of append to one another. So you get like a chunk and then another chunk from this second female model, and then you get another chunk from this all model. And since they all have the same columns, rbind just stacks them all together. So from this, you get a table here. And that's kind of what happens when you use rbind. It's going to stack together all of the rows. And here I've sorted it again by the term so that it's easier to compare all of the intercepts and all of the height effects. So, yep, Lenka is exactly right. rbind stands for row binding, and cbind stands for column binding. So it's like one of them you're stacking every row on top of one another, and then another one you're binding columns onto one another. Now these aren't tidy constructs, but they're one of the more useful things that I find, at least in R, especially when you're programming with groups like this. So rbind and cbind. I think I've used that before in the course so far. Anyway, so I've got this collection of estimates, and I've asked you a couple questions about their interpretation. So I've asked you, are the effects statistically significantly different? Well, the effect for men only is this row, and that's the effect of height on earnings. So an additional meter of height gives them 31, I think it's dollars extra per month on average. Now, obviously people don't grow 31, or maybe it's 31,000, but obviously people don't grow a meter. That's like an unrealistic amount to suggest that height changes by, but that's kind of the interpretation scale we're working on. And I think that that's thousands of dollars per month or maybe per year, I'm not sure. So the confidence interval around that estimate is 15.736 to 47.06, right? So that is 31 plus 2 times 7.9 gets us to 47, and 31 minus 2 times 7.9 gets us to 15. Okay, so that's how these are constructed. And likewise, you can see that for the women-only model. The effect of height on earnings is 16, but it's somewhere between 7 and 25, with 16 being our single best. Finally, the estimate for the overall is 63, and plus or minus about 6. So its suggestion is 57 to 69. That an additional meter of height has that impact. Now, the thing that immediately should tell you that something weird is going on is that when we estimate the linear regression for each of the groups, every single intercept is different from one another. So the overall model is somewhere between the men only and women only, and it's statistically significantly different than the men only and women only model. So the intercept suggests that there's quite a strong amount of heterogeneity in the average earnings or in the baseline earnings. So you can tell because this interval does not overlap this interval. 16 is less than 24. So the highest value that our women-only intercepts can take in that confidence interval is still smaller than the smallest value the men-only intercept will take at that confidence level. And likewise, for the overall model, it's very tight. It's very precisely defined. For the slope, why am I looking at those confidence levels and not the ones below? What do you mean the ones below? I'm just talking about the intercept right now. I'm about to talk about the height-centered ones because these are the slopes. So for the slopes, for the height-centered ones, the confidence band for men only is somewhere between 15 and 47. The confidence band for women only is somewhere between 7 and 25. 15, the kind of lowest value that we would expect the men's estimate to get, is actually lower than the highest estimate that we would expect the women's to get. So therefore, if the men's true value were actually at 15.73, then that's within our level of uncertainty about the women's estimate. The confidence intervals overlap. Therefore, we can't say that they're different from one another at the 95% confidence level, at the confidence level in which we're using here. Okay, so if these overlap, then you can't tell them apart. If they are what's called disjoint, if they don't touch, as the intercepts don't touch, then you can tell them apart. This is the 95% confidence interval I'm showing here. If you use the 99 or the 90 or the 80, that's fine. Just explain to me what level you're using in your analysis and use that level consistently. Okay? I really, really don't mind, even if you wanted to be a jerk and use like the 60%. If the question said Isabel, you only needed to talk about what was in the question. I was just talking about the intercept for to make the explanation more clear. I'm just kind of walking you through the concepts to make a full explanation of what's going on. Okay, so the question only talked about the slope. So if you only talked about the height centered, that's fine. But I'm just showing you that the height centered is not different for men and women. You know, they overlap, but the overall is extremely different. In the intercept, all of the intercepts are different. Now, this is important because all of our p-values are incredibly small. So all of the effects are statistically different from zero. But that does not mean they are different from one another. And that's the important takeaway here. Sometimes we can say, ah, yes, men definitely have a higher baseline earnings in this data set than women. Other times, we can't say that the extra meter of height has a different impact for men than for women. That conclusion is not statistically justified. Okay? If you wanted to show this graphically, there are a couple ways you could have done it. One package that I used to teach is the dot whisker package, but the reason why I don't teach it anymore is because it can silently kind of fail to show you what you think you're showing. So I'm just showing you here, this is a graphical presentation of what we were just talking about. So the confidence interval is the line and the estimate is the dot. That's all right, Emily, I don't mind F's in the chat. In this case, you can tell that estimates are different when their confidence intervals do not overlap. However, in the case of the intercept, you see that all of these are disjoint. So a plot like this is sometimes again called a caterpillar plot or a dot whisker plot, and you can make them in ggplot yourself by doing plus and minus 2 standard deviations, and the estimate is a geom point. I don't expect you to do that. It can be very complicated to do this correctly. So I just wanted to show you graphically that this tells you the same information as that. It's just this one you're thinking about the numbers, and this one all you have to do is compare the lines. Okay? So the correct answer here is that men and women have approximately the same effect of an additional meter of height, but the overall model is way off from both of them. So something weird is going on. Sophia asks, where did the variable results come from in dot whisker? Right here. If you'd like to run this yourself, I think you can change the HTML to RMD, and you'll get a R Markdown file that you can see everything that I'm doing there. Okay. I try not to have very many hidden blocks, but like this one is a hidden cable. So anyway. Okay, so that's 1.1. 1.2, why would the impact of height on earnings be so much larger for the data overall than for men and women as a subset? So here I suggested that you make a scatter plot. And this shows the line for female in green, the line for male in blue, and the line for everybody in red. The issue here is that men have both a higher baseline earnings and a higher baseline height. So they're off to the right and up from the group of women as a reference category. What this does is cause the model that considers all the data to be too sensitive to the difference between those groups. So the slope overall is way too steep. An additional meter of height shouldn't make someone earn 60,000 more. Men and women both have the same estimates in their own groups, but when you pool without taking account of heterogeneity, you're going to get an invalid result, the red line. Okay? So that's what this is showing. And so I've written up a short explanation. In order to fit the same line through both groups, the overall regression has to be much steeper. Now, there's another kind of thing that we can talk about. If I can get my iPad up and connected. Hold on. I came prepared today. You'll be happy to know. Okay, and then my iPad. Okay, so I just want to show a more kind of schematic version of this. So I'm going to switch the application I'm sharing to be my iPad real quick. Okay. So in a really exaggerated way, what's happening in this data is that I have one pattern, let's say women down here with lower heights and lower baseline earnings, and one pattern up here. Actually, let's move them a little closer. And one pattern up here, which is the men, with higher heights and higher baseline earnings. If I fit a line through the clouds separately, I get lines that look like this, let's say. Approximately the same slope, but different intercepts. If I ignore the fact that they're in different groups, and I try and fit a line all together, I'm going to get a really funky line. So this is the classic case for using multi-level models, is when you have a configuration of groups or points or things like this that suggests that the slope needs to be different or the intercept needs to be different for different groups. One could imagine a scenario where as well, in the men's case, what if our point cloud looks like this? Our overall line would still go through both of them, but the men's line might even look like that. So that's the point of these kinds of varying slope, varying intercept models. If you're trying to compare between groups, and those groups have different behaviors, then you might need to come up with a way to allow them to pool their information together, but you definitely don't want to get this line. Does that make sense to everybody? So that's that's kind of the best form answer for that question. Now, of course, everybody is different. And if your explanation focuses on kind of aspects of this plot, or maybe things about the way that these points are configured and stuff like that, then that's okay. You know, there's a continuum of the interpretation of this kind of thing. But the main point is that it looks like men and women actually have the same relationship between their height and earnings, but have different baselines. Zoe asks, could you describe it as clustering? Hell yeah, you can. In fact, economists call multi-level models error cluster models. So yeah, if you use that term, you're doing really well. Am I using height or mean-centered height for the scatter? I'm using raw height, but if I used mean-centered height, all that would happen is I would get a 0 right in the center here, and then it would go negative and positive. Literally nothing else changes about that. You're just shifting the location of 0. It doesn't change anything about the shape or pattern of the points. I'm using the regular height, but it shouldn't matter. Okay, was it appropriate here to comment on other practical factors that make males and females different with height and earnings? Yeah, sure. That's fine, but you would need to also kind of engage with the central question that, numerically speaking, you see that something's up here, and it looks like the issue is that your all regression is ignoring the heterogeneity between groups. So if your explanation focuses on the reasons between that heterogeneity, that's fine. But kind of the main point that has evidence empirically is that the two groups are different. They appear to have different baselines, but have about the same slope. Moving to 1.3, unless anybody else has questions on, can centering change the statistical distinctness of the intercepts? It can, Finn, yes. So imagine if you have two really, I can talk about this later in detail if you'd like, but yesterday I showed some examples of where when you change or actually in a previous lecture as well, when you change the location and you shift this axis, this height axis, left or right, if the two lines have different slopes, it can actually change which one is bigger at the intercept. So you can have a model where you fit it on the raw data and say the intercept for men is bigger than the intercept for women. I center the variable, that relationship flips. Last year I used that example in a data set for this chunk, and it blew some heads up, so I picked a little simpler of a one. But that can totally happen. The intercept is just a description about your prediction when x is 0. So if that meaning of when x is 0 changes, you can totally get a reversal of that trend, or that prediction of which one's higher at that value. Okay, so fit a fixed effect model so that men and women have different baseline earnings, but so that height has the same effect on men and women. Does this give you a more reasonable estimate of the effect on height on earnings? Also, according to your regression, what is the difference in earnings between a 17.5 meter man versus a 17.5 meter woman? Or not 17.5, 1.75. Well, I mean, the difference would be the same, but that would be a very, very big, maybe they make a living as a statue model or something. Yeah. So the fixed effect model here would be spelled 0 plus height, and here I'm using height centered, plus sex. Okay, so this is the fixed effect model. And these are the results that you get from a fixed effect model. In this case, I recover the different intercepts for men and women, but I recover a height estimate of about 23. Thinking about the values that I got from above, the male estimate was 31, which was somewhere between 50 and 47. and the female estimate was somewhere between 7 and 25. So 23 is actually a pretty good guess for the slope, including both men and women, so long as I take into account the heterogeneity in the intercept. I think, Cracker, I think Noah means he's been eating vegetables. So the point here is that once I take into account the difference in intercept, the slope is pretty reasonable for both groups. The slope I get is actually in the confidence band of their separate models. So this should give you more evidence that the issue here with this data set is that they have different baselines, but the effective height is the same. Okay? Now, I've also asked you what's the difference between a 1.75 meter man and a 1.5 meter woman. So to do this, you do the same thing we've done for a while in the course. You build a scenario data frame that has the predictions you want to compare. We have the same heights, but we have different sex. I'm also forcing that to be centered because the model was fit on centered data. So if this is specified in terms of the raw height, my scenario needs to be specified in terms of the mean height. I suggested that you be very careful in this. So if you have done a prediction, that's good. But if you forget to do this, that might be sort of a point off. But then if you get the right answer, which is 11.53, you'll do okay. And you can see this directly if you just look at the contrast model, which fits the difference of men relative to women. So there's a lot of different ways you could get to this place. If you chose to do it using the prediction, then I'm going to try and make sure that you use the correct X variable here. Or you could go for this directly and then say, well, I don't want to deal with doing prediction and these two models are equivalent, so I'm going to use the contrast model. Either way, just as long as you get the valid result and you do that in a correct way, that's fine. But the important realization here is that your raw height is not going to be the same after you subtract off the mean. Okay? So, 1.4. Fit a multi-level model using LMER that allows both the baseline earnings and the impact of height on earnings to vary. So for this, I'm looking for a model that has both a varying intercept and a varying slope. In the answer key, I have omitted the +1 in front of the height centered because that's done automatically. It's okay if you put that there. It's the same model. And you can see I'm using the double pipe here. That's because there are only 2 sexes in this data. And you have to kind of account for the fact that that makes it very difficult to estimate correlations between the slope and the intercept, as we talked about yesterday. If we had more responses that had different groups for that variable, then we'd be able to estimate the correlation. So richer data means that you can do better analyses. But here, we only have 2 categories in that response variable, so we have to do this independent. The set of fixed effects can be gotten directly from the tidy output, and the set of random effects can be gotten using the mermod with ran coefs. You could also do this using ranf. Same thing. Okay, just as long as you show me what are the random components and what are the fixed components. Here, I'm showing you the mixed components, technically. Okay. I'm also showing you a dot plot using lattice, like we did before. That indicates that the baseline is different for our 2 categories, but the height is not. Does everybody see that? The U effect is on the left with the intercept, and the W effect is on the right with the height. Continuing on, I ask you to fit a generalized mixed effect model that predicts whether a respondent has income, depending on their sex. Allow both the intercept and the effect of sex to vary by education level. Okay, so this, I think, was the first point where people got a little bit tripped up in mechanics of using R. So what you needed to recognize, and I think I talked about this in class, but my point was, that every place where the earnings was 0, that's counted as not having income recorded. And then NA is also counted as not having income recorded. So if you did this using only earnings equals 0 versus earnings not 0, you'd have a bunch of missing data. And that's okay if you fit it that way, but that's not exactly what I was talking about. So I was talking about whether or not a respondent has income. Missing data means that their income is not recorded. So we can't tell if they have an income. So the way that I did this was here. I made a binary column that indicated whether or not earnings was greater than 0. And then I replaced all of the NAs in that column with 0. 2 steps. Is the earnings greater than 0? If data is missing, replace that with 0. One of the very first things that we taught you about R was that a statement like NA greater than 0 comes back as NA. So that's how this works. If you do this in the other order and you replace the NAs in the earnings data, and then also say earnings greater than 0, you get the same result. Okay? So I don't care really how you did that, as long as you did that. Then, to fit this model, we use the same kind of concepts that we learned using LMER, and the same kinds of code that you learned in GLM, and mash it together. So this is the synthesis action for this assignment. We use the function glmer, which is GLM and LMER mashed together. We use a LMER function, but we give it the binomial family to tell it that it's a binary model. Okay? Does everybody see that? It's the same thing that you've done as a GLM and the same thing that you've done as an LMER mashed together. Cool. I screwed up my formatting. Note that because we have multiple different kinds of education categories, we can use a single pipe. This should estimate fine. If you used a double pipe, that's okay too. You might get different results. I ask, then, what are the fixed and random components of the model? Well, we can do that in the same manner as before. You get the fixed components using tidy. You get the mixed components using rancoFs or ranpars, either way, or ranf, either way. So I just wanted to see these, that you got them correctly. And then I asked, what is the predicted probability that a respondent in each group has their earnings recorded? So what is the predicted probability of a respondent in each group having their earnings recorded? The way that I hinted that you should do this, is it bad that you only get sex male and not sex female? You just fit it in a contrast form, and that's okay. So you see in my model, I only have sex male. So if you fit it in the fixed form, that's fine. You're going to get different numbers. Yes, Georgia, it means that the intercept is sex female, and this explicitly is the difference between sex female and sex male. Cool. That's why I fit it in the contrast form, because I knew that we would need it later. So, but you can do it however you want. So I then ask you to build a grid of all possible combinations of education and sex. Or I ask you for the prediction in each of those unique categories. And this, I think, proved to be more challenging than I actually expected it to be. So my hint to you was to use expand grid on the unique values that you could obtain. So you see here, I've gotten the unique education levels. And then I've gotten the unique sex levels in my data. Using expand grid, I say I want education according to my education levels, and give me every combination of those with the sex levels. So my output data has the first category as female, the first category as male. Then it moves to the next education level and gives me that as female and that as male. Then it moves to the next education level and gives me that with our two other categories, and so on. That is all expand grid does. My hope was that you would just play around with expand grid, learn a little bit about how it works, and then use it, or read the documentation. It's okay to experiment with these kinds of things. So that's why I recommended that you use expand grid. The other way that I heard that people did this was they got the predicted probability for every person and then computed the average or median inside of each group. That works in this case because all of the variables are categorical. So all of the variables, all of your predicted probabilities for secondary educated females are the same. All of your primary educated males are the same. So if you get the mean of 100 identical elements, you're going to get back that element. So that actually works as well. But this is what I meant when I said using expand grid. You pop that into the predict function like we did last time for the logit, and you get the predicted probability. Donezo. So the challenge here was, do you know how to construct this frame? Or did you do it manually? Or did you do it in some other way? This is something you saw this week that literally everybody did right at one point. And then I'm arranging it here so that you can see the result. Okay? So that's all I was asking for there. If I'm a primary educated male, what is my predicted probability of having an income recorded? If I'm a postgraduate educated female, what's my predicted probability of having an income recorded? Going to part 4, interpreting the table from the previous question, which levels of education have the largest difference between men and women in the probability that an income recorded, and which levels have the smallest? Why do you think this pattern occurs? Oh, that was supposed to be a U shape, not an N shape. Lowest probabilities for the primary and PhD educated groups, and the highest in the middle. Okay, so that's what we see. When you compute the difference, there's a lot of different ways you could do this. You could pivot it wider. Here I'm using a group by and a summarize, whatever you want to do. So conceptually, this is the same as the challenge question from our first chunk. So for those of you who thought of this and didn't even think it was a challenge, you're doing really well. This was the conceptually same thing that we did in the challenge question in the first part. And now you're doing it in your sleep, hopefully. So we get this frame where we get the differences between the groups. And this one is always computing the difference between men and women. So if it's positive, it means that the male probability is higher than the female probability. And you can see that from our results here. For PhD, the difference is about 5. For postgraduate, the difference is about 10, maybe 13, and you can see that in the table here too. How does it know to do between men and women? Okay, so diff just takes every element and subtracts it from the next element. Okay? Tidy, the whole tidyverse, is always going to try and sort your data before it does anything. So it thinks about structured comparisons, and it always tries to make sure that things are sorted with the slowest moving on the left and the fastest moving in the right. You can see that here, slowest moving, fastest moving. Okay? So when I split the data frame by education level, I get this data frame, this data frame, this data frame, this data frame, and this data frame. Notice that because the tidyverse has built this data frame in this fashion, it always goes female, then male, female, then male, female, then male. The diff is computing the difference between those two elements. So it's always going to do it in that order. And I guess it's actually going male minus female. Okay? So we get this result. Now, I'm showing you a visualization of this here as a bar plot. Now, we've made a lot of histograms, but I've never taught you how to make a bar plot, and you'll learn about this next week. You'll see that I'm also using a very interesting option here that you may never have seen, which is that stat is equal to identity. For every geometry, you can actually change the kind of statistic that it's computing as a summary. So ggplot is actually a very flexible kind of way of demonstrating statistical results. And we'll talk about that a little bit next chunk. Every statistical analysis has a equivalent visualization. So in this case, I'm just showing you the graphical presentation of that table, where the PhD bar is 0.05 high. Okay? A much more complicated way to show this difference is using a dumbbell plot. In a dumbbell plot, you're showing the difference between two groups as the line connecting two dots, hence why they call it a dumbbell. So here I've visualized the female dot in red and the male dot in blue, and the predicted probability that a person has an income is on the x-axis, and the education level is on the y-axis. The length of the line corresponds to the difference between the two groups. Okay? You can see that it's tightest for primary and PhD, and in the middle, it's about the same length with the highest being at secondary. As someone suggested, this is a bit of a Nike swoosh. Goes down and then up. And the lengths also do that kind of generally the same thing. So all I was looking for here is a recognition that this is happening, and then maybe a short explanation as to why you think it might happen. So something that you could say might be, you know, the data set has more missing values for primary people overall, regardless of their income, so there might be an issue with that. So it could be that, you know, people with a primary education are hard to sample, people with a PhD are rare, so generally they're hard to sample. You could say that, you know, if I am a woman and I get a PhD, it's going to be very unlikely that I'm going to, you know, not work and not respond to a survey, because I both value science and have been highly trained. So I might, you know, be much more interested in trying to make sure that I, you know, am working, or I might have more job opportunities available to me. Whereas kind of in the middle range, there's more of a likelihood that you're going to be in a single earner household. And then in the bottom, there's more of a kind of likelihood that both people will have to work in order to make enough money to survive. So just a kind of a simple thing that falls out of this national election earnings survey. And that's all I wanted from that. So you can interpret this, using a variety of kind of explanations, but my point was I wanted to see you get here and then give me a real plain English explanation of what it is and why it might be the case. Even if it's a completely outlandish explanation, I just want to see you connect it to real social thinking. Because again, the point of this is kind of using empirics to make arguments, okay? Not just about getting the number, it's about understanding what the number means. So that's it. That's the assessment. Hopefully by now, you kind of get a sense of how I structure these things. You've done 3 of them so far. It's always going to be something at the beginning that is an exploration of the model, something in the middle that demonstrates a problem with a naive analysis, and then something at the end that resolves this problem or kind of illustrates it. Okay? In this case, the problem that we had identified was this issue, and then we quickly fit a model that corrected for that, which is either this one or the multi-level model. Okay? And then 2 kind of was added on because I wanted to see you do a GLM in multi-level. Sound good? Are there any other questions? I will teach you how to make a dumbbell plot if you want. The code is here. It's kind of nasty because you have to, you'll see it in the source code if you grab it. You'll have to, oh, did I forget to post answers to the challenge? I might have. Yeah, I can go through the rock curve from the last assignment, Matthew and James. Could I use a different visualization for 2-4? Yeah, you can. You can do whatever you want. I didn't even ask for a visualization. So if you did that, you're doing great. Yeah, so I'm sorry I forgot to do the challenge. I actually don't want key. I want the rock curve. Did I forget to do the rock curve here? Oh, I didn't make the rock curve there. So yeah, let's see. I don't. Okay, so let's do it on the fly. Okay. So everybody see this here. I'm going to zoom in. I know that it's small. Okay, so here is my dumbbell plot stuff and all that fun. Okay, so to make a rock curve, the first thing that I need to get are my predicted probabilities from the actual observations. So I might need to say predict, what did I call it? Missing model type is equal to response. Okay. So just to show you what that looks like, I'm going to make a histogram. Oh, so those are my predicted probabilities, right? And you can see that each group has the same probability. So that's why we get all this kind of chunkiness in this histogram, because there's only one category here that has all the same predicted probabilities. Another category there that only has the same probabilities, right? And in fact, we might be able to say color is equal to earnings as income. No, what was it? Education. So you can see there, these 2 groups are the primary. It's really probably should be fill. There we go. Yeah. So just as a quick plot, you can see that. Sorry if I'm keeping on scrolling around. It's kind of hard to get everything on the screen. Okay, so the first thing you need is that probability. The second thing is the plot rock package. Okay? And the plot rock has a couple of functions. But the main one is this geom rock, yeah? So what does geom rock do? It displays a empirical rock curve, useful for characterizing classification accuracy and continuous measurements, okay? So if I scroll down to the examples, okay, some of you just copied this straight and said, hey, look at my rock curve. That's a bummer, because the first thing that this is doing is drawing 50 random observations with a probability of 0.5 from a binomial distribution, which is like a Bernoulli distribution. So you literally just showed me the rock curve for random data. And I can understand. The point of kind of doing this exercise, though, was to try and show you that the rock curve relates the prediction probabilities from their accuracy. So if I want to use the ggplot to do that rock stuff, I would need to send it earnings, where my probabilities are added to the data frame. Okay, actually, I'll do this up here because it's easier. So my probabilities are named probabilities. Okay, so to use plot rock, you do ggplot and earnings, and I'm going to add the probability to it. So I've got my probabilities. Now, in the documentation here, the ggplot, or the components of the AES aesthetics that it needs, are down here, Y and X. The other way to deal with this is by providing the variables they call M and D. So M is the probability, and D is the outcome. So AES, M is equal to probability, D is equal to has income, and then we do plot or geom rock. And that's the rock curve for our data. So our model is better than chance, but it's not very good. Okay? So the geom rock takes the M as the probability, which is like the mean, and then D is the binary variable. Okay? You could also use something like, I think it's P-rock. There's a package that people were using. I don't really care how you were getting it, but the way to use the plot rock was that. And then P-rock, I think it's yeah, as long as you sort of explain what you're doing. It's not a rock curve, obviously, but the accuracy curve is different. The accuracy curve is just the percentage of correct guesses at the individual threshold. So you can do that using the same kind of code that you had before, which would be something like for sequence, let's say from 0.4, let's say from 0 to 1 maybe. Let's say 0.01 to 1 by, let's say 0.02. you might, define the accuracy function that we had in the last lab, which, what was it? Something like that. Or there might be a built-in somewhere to do this as well. So you define that. Data is equal to earnings now. The model is equal to missing model. And then we would say our accuracy is equal to So to break this out, what I'm doing is I'm computing the accuracy for a given threshold and then saving that into a list that I'm going to call accuracies. So it's like every time I'm computing a new accuracy and storing it at the end of my existing accuracies. So this will string along, or what's called concatenate, this vector with this vector. Okay, so if I wanted to compute, that curve, I would need to define that function. And then of course, is freehold isn't found, it has income is what I want. And then it's computing this, or is it not? Team sequence is freehold. So where am I still using as freehold? So then I've got the accuracies. And that's my curve. Can make it prettier, but that's it. So you just pick a couple of thresholds and you compute it, and then you make that plot. Okay? What are the points labels in the rock curve? Let's split this off. Are you talking about these points here? I think that they're just, I think they're standardized quantiles for showing the prediction accuracy, but I'm not quite sure. You'd have to check the documentation of the geom rock, because it's probably controlled by an option. Maybe cutoff labels. Yeah, cutoffs that. So it's just the default for the cutoffs that it's showing. Okay, so the rock curve is computed across all thresholds. You don't have to enter in like a specific censoring of it. It's just the probability and then the actual answer, and so it'll show you the rate at which those two relate. Okay, and for the accuracy, you're always just looking for the set of accuracies you're just looking for the accuracy at each threshold. And it's okay if this is a bit too advanced. You could do this other ways as well. There might be a built-in function in some of these packages to compute the threshold curve. I'm just showing you if you did it from scratch, that's how it would look. And again, it's a challenge problem, so that's the accuracies versus thresholds. So if we set our threshold to say everything is positive, we get an accuracy of 60%. If we go up to a threshold of slightly above 0.5, we get a little bit better. And then as we increase the threshold to get stricter, we get very inaccurate. So that's the accuracy. The ROC curve is here. And its optimal is also somewhere around 0.5, maybe that there. So cool. Okay, well, that's the answers.